This is our second lecture of chapter 12, Liquid, Solids, and Intermolecular Forces. So last time, we had covered the properties of liquids and solids. We had seen intermolecular forces in action, specifically in liquids, showing up or having an impact on the surface tension and the viscosity. And then we also looked at phase changes. And of those phase changes, we looked at evaporation and condensation. And that is a phase change between liquid and gas, or gas and liquid. The phase changes of melting and freezing. Those are the phase changes between solid and liquid, or liquid and solid. And sublimation. Sublimation is the phase change between a solid into a gas. In this part of the lecture, we'll be completing a chapter and we'll be looking at the specific types of intermolecular forces. Then we'll be looking at different types of crystalline solids. And then lastly, looking a little bit closer into water and why it is so significant in regards to its intermolecular forces. So the strength of these intermolecular forces between the molecules or the atoms that compose a substance, that'll determine the state, whether our substance will be a solid, liquid, or gas, of the substance at room temperature. When we have strong intermolecular forces, they tend to result in either liquids or solids, and liquids and solids will have a high melting point and a high boiling point. And this is due to those strong intermolecular forces. When we have weak intermolecular forces, they tend to result in gases. And these gases have low melting point and a low boiling point. So the weaker our intermolecular forces are, even between one state, the weaker the intermolecular forces are, the lower the melting point will be and the boiling point will be in regards to a similar compound that has stronger intermolecular forces. So here we're going to focus on 4 fundamental types of forces. 3 of these are our intermolecular forces. Intermolecular forces are the forces that are happening between different molecules. And then we'll consider another type of force that's not considered an intermolecular force, but it is a force. So between our intermolecular forces, our weakest intermolecular force is our dispersion. The next strongest is the dipole-dipole intermolecular force. And stronger than that usually is our hydrogen bonding, if we have hydrogen bonding. And these are our 3 intermolecular forces. And then we have a 4th force, which isn't necessarily happening between molecules. It's considered our ion dipole. So the ion part happens between an ionic compound. So for this reason, we do not consider this an intermolecular force, but this type of force is generally stronger than all of our intermolecular forces. So again, the types of intermolecular forces are dispersion forces, dipole-dipole forces, and hydrogen bonding. The dipole forces are going to occur between all molecules and atoms. And this is due to the instantaneous fluctuations in the electron charge distribution. So at any moment, we may see that we end up having a higher concentration of electrons on a particular side of the atom or molecule. than we have on the opposite side. So then we have a difference of electron charge distribution. For dipole-dipole forces, these dipole-dipole forces will exist between molecules that are polar. And then hydrogen bonding will exist between molecules that have a hydrogen directly bonded to either a fluorine, oxygen, or nitrogen. And these hydrogen bonds are going to be the strongest of these three intermolecular forces. First, let's discuss the dispersion force. As we mentioned before, this intermolecular force is going to be present in all molecules and atoms. It's also sometimes referred to as the London force. These dispersion forces are caused by the fluctuations in the electron distribution within molecules or atoms. So at any one instant, the electrons in an atom or a molecule may be unevenly distributed. And when they're unevenly distributed, these electrons are constantly flowing around. So this fleeting charge, which only happens for a moment at a time, but can happen over and over again very rapidly, this charge separation is called an instantaneous dipole, which means we have a very temporary dipole. So if we look here, we have a helium atom, and at any point, if we look at frame 1 in regards to frame 2, we see that the electrons are constantly moving around. And these electrons, these two electrons, are not necessarily going to be directly opposite to each other. In frame 2, they look to be directly opposite to each other, but at any one point, they could be closer to the same side as each other. And if they are, we overall have a higher electron distribution on the left side of this atom that we see here. And because we have a higher concentration of electrons on the left side, this is temporarily causing a negative dipole moment, or a negative dipole. On the opposite side, we have less electrons, and so that is temporarily having a temporary positive dipole. So what happens is that instantaneous dipole that just occurred on one of those helium atoms, now it's going to induce an instantaneous dipole on the neighboring atom. So on this last slide, we saw that one helium atom had a partial negative charge on the left side and a partial positive charge on the right side. As it gets close to its neighboring atom, the partial positive end of that atom will induce a partial negative end of the next atom. And because now we have an induction of a partial negative end on one side, it'll cause a partial positive end on the opposite side. And then the neighboring atom will then induce an instantaneous dipole on its neighboring atom. This attraction is called the dispersion force. So the dispersion force occurs as these neighboring atoms are attracting one another, where we have the positive end of one instantaneous dipole that attracts the negative end of another. The dipoles that are responsible for this dispersion force are transient, and they're constantly appearing and disappearing in response to the fluctuations in their electron clouds. Now, the magnitude of the dispersion force will depend on how easily the electrons in the atom or molecule can actually be polarized. In other words, how easily they can form a dipole moment in response to the instantaneous dipole of its neighboring atom. And this will depend on the size of the electron cloud. The larger the electron cloud, that'll result in a greater dispersion because the electrons are held less tightly by the nucleus, and therefore those outer electrons can polarize more easily. So while molar mass alone doesn't determine the magnitude of the dispersion force, it can be used as a guide when we're comparing dispersion forces within a family of similar elements or compounds. So we see here in table 12.2 or 12.4, we're comparing the boiling points of all noble gases. These are arranged from the noble gas with the least amount of mass to the largest, highest mass of noble gases. And because we can compare a family of similar elements, we can compare these, and we see that as we're increasing in molar mass, we see that their boiling point is also increasing. Remember that the boiling point increases as we have stronger intermolecular forces. So that means that because noble gases can only have the dispersion force, intermolecular force, it means that as we're getting into larger and larger clouds, remember that these electrons are held less tightly by the nucleus and therefore they can polarize more easily, which means that they have an increasing dispersion force. And that's why we see an increasing boiling point as these electron clouds get larger. The second type of intermolecular force that we're learning about that is stronger than the dispersion force is the dipole-dipole force. And the dipole-dipole force is going to exist in all polar molecules. It'll be similar to the dispersion force in that there is a dipole-dipole attraction, except that in the dispersion force, that dipole-dipole attraction was just temporary. But in polar molecules, these dipole-dipole forces or attractions are permanent. So these polar molecules will have permanent dipoles that will interact with the permanent dipoles of neighboring molecules. So what will happen is a positive end of one permanent dipole will be attracted to the negative end of another permanent dipole. And this attraction is called the dipole-dipole force. So if we see here, we have the molecule HCOH. What we see is that we will have we end up having a partial negative end on the oxygen, and we end up having a partial positive end on the carbon. So what we see is that that partial positive end that's on the carbon will then attract to the partial negative end on the neighboring molecule's oxygen. And this will attract these two molecules to each other. And this is called the dipole-dipole force. These additional attractive forces will raise their melting and boiling points relative to the nonpolar molecules of similar molar mass. So if we have a molecule of a similar molar mass to this molecule that's shown here, but the other molecule does not have dipole-dipole forces, that means that the only force that it does have is the dispersion force, whereas this molecule here has the dispersion force as well as the dipole-dipole force. So because this molecule will have the stronger amount of attractive forces, it will see a higher melting point and a higher boiling point than that nonpolar molecule that had the similar molar mass. So here we can see the effective difference in polarity on melting and boiling points for two compounds of similar molar mass. Here we have formaldehyde, which is a molecule that we saw in the last slide. And then we also have ethane. These have similar molar masses of about 30 grams per mole. Ethane is only composed of carbons to hydrogens. And remember that carbons and hydrogens have similar electronegativities, as well as their structure, which leads to having a nonpolar molecule overall for ethane. Whereas formaldehyde, we saw, is a polar molecule. So ethane, its intermolecular forces are only the dispersion forces, whereas formaldehyde has dispersion forces as well as dipole-dipole forces. And for that reason, we see that formaldehyde has a higher boiling point of negative 19.5 degrees Celsius, whereas ethane had negative 88 degrees Celsius. And formaldehyde also has a higher melting point of negative 92 degrees Celsius, whereas ethane had a melting point of negative 172 degrees Celsius. Now, miscibility is a liquid's ability to mix with another liquid. In general, polar liquids are going to be miscible with other polar liquids. Similarly, nonpolar liquids will be miscible with nonpolar liquids. But usually, polar liquids are not going to be miscible with polar liquids are not going to be miscible with nonpolar liquids. So for example, if we have water, which is a polar liquid, it is not going to be miscible with pentane. Pentane is only composed of carbons and hydrogens and is a nonpolar molecule. So this polar liquid is not going to be miscible with the nonpolar pentane. Similarly, we see that water and oil do not mix. That's because water is polar and oil is nonpolar. This is the reason that oily hands or oily stains on clothes cannot be washed away with plain water, because these oily hands or oily stains are made up of nonpolar molecules, whereas plain water is made up of polar molecules. In these pictures on the bottom left, we see in figure A, we have pentane that's not mixing with water. So pentane is forming its own layer and water is forming its own layer. In figure B, we see that the oil and the vinegar in salad dressing separate into distinct layers. So we have a layer of oil and we have a layer of vinegar, but they do not actually mix up with each other. And then in part C, we see an oil spill from a tanker that contains petroleum now spilled onto the seawater are not miscible. So all of that oil generally floats on top of that water. We need to know how to determine if a molecule is polar or nonpolar. We had done something similar in a previous chapter, but we should review it here. First, we want to determine whether the molecule contains polar bonds. For that, we need to look at the electronegativities of both of the atoms that form that bond. After that, we want to determine whether the polar bonds will add together to form a net dipole moment. So again, for number 1, to determine whether the molecule contains polar bonds, we'll need to check the electronegativity differences between the two atoms that form that bond to see if that bond is polar or nonpolar. If we look at CO2, which is your top right atom here, or top right molecule that's shown here, we see that CO2 does have polar bonds. So between each of these carbons and oxygens, there is an electronegativity difference that's greater than 0.4. The oxygen has a greater electronegativity. So the polar bond has an electronegativity that attracts more to the oxygen end. Similarly to the other bond, the other C double bond O bond, we have an electronegativity difference of greater than 0.4, and oxygen is more electronegative, which is shown by these arrows that are drawn here as well. Because these have the electrons pulling away opposite to each other, directly opposite to each other, these overall cancel out. So CO2 itself is a nonpolar molecule. If we look at CH2Cl, CH2Cl2 does have polar bonds. When we draw out the geometry of this molecule, we'll see that this molecule is tetrahedral. And we'll see that the carbon to chlorine bonds are more polar than the carbon to hydrogen bonds. So we do not have an even distribution of the pull of electrons. And for that reason, this molecule is polar. And then lastly, let's look at the example of CH4. CH4 is also going to make a tetrahedral compound where all of the bonds are between our carbons and hydrogens. And they're all evenly distributed from each other, or evenly spaced from each other. In this case, carbon to hydrogen, the electronegativity is so small that we do not consider that a polar bond. But also because these are evenly distributed, or evenly spaced from each other, they would also cancel out anyway. So overall, this molecule is a nonpolar molecule. The strongest of our intermolecular forces is the hydrogen bond. Polar molecules that contain the hydrogen atoms that are bonded directly to fluorine, oxygen, or nitrogen, they exhibit an additional intermolecular force that's called a hydrogen bond. So for example, HF has a hydrogen bond intermolecular force, NH3 has hydrogen bonding, and H2O also has hydrogen bonding. So a hydrogen bond is sort of like a super dipole-dipole force. So the reason that a hydrogen bonded to a fluorine, nitrogen, or oxygen can do the hydrogen bonding is because of the large electronegativity difference between the hydrogen and these very electronegative elements. And the small size of these atoms will allow the neighboring molecules to get very close to each other. As a result, we form a very strong attraction between the hydrogen in each of these molecules and the fluorine, oxygen, or nitrogen on the neighboring molecule. So again, the intermolecular attraction of a hydrogen atom to an electronegative atom, specifically the nitrogen, oxygen, or fluorine atom, is called a hydrogen bond. If you look on the top left, we see that we have different HF molecules. The hydrogen in this molecule is forming the partial positive end, and the fluorine is forming the partial negative end, because fluorine is much more electronegative than is the hydrogen. Fluorine has an electronegativity of about 4.0, whereas hydrogen has an electronegativity of about 2.1. That partial negative end of the fluorine is going to be attracted to the neighboring molecule's partial positive end from the hydrogen. And this will continue between the neighboring atoms. On the top right, we see the hydrogen bonding between different water molecules. In water molecules, remember that these are not linear structures. The molecular geometry is a bent geometry. And each of our hydrogens has a partial positive charge, and each of our oxygens has a partial negative charge. And the partial positive charge of the hydrogens is going to be attracted to the neighboring atom's partial negative charge on the oxygen. And the partial negative end of the oxygen is going to be attracted to the partial positive end, or the hydrogen, on the neighboring atom. We see between methanol, we also have the hydrogen bonding, which has attractions between the hydrogen that's bonded to the oxygen. That hydrogen has a partial positive charge, which is attracted to the oxygen of the neighboring atom, which has the partial negative charge. Notice that these hydrogens do not form these attractions of hydrogen bonding. These hydrogen bonding occur between the hydrogens that are directly bonded to an oxygen, nitrogen, or fluorine. And then this hydrogen that is bonded to one of those atoms is then attracted to the neighboring atom's oxygen, nitrogen, or fluorine. We see that hydrogen bonding also occurs in the double helix structure of DNA. So we see between thymine and adenine that this hydrogen that's bonded to a nitrogen in one molecule has a hydrogen bond attraction to the nitrogen of the adenine. And it's these type of attractions that keep these double helixes, or these two helixes, attracted to each other to form this double helix. Here we can see the effect of hydrogen bonding on melting and boiling points for two compounds of similar molar masses. Again, we're comparing to ethane. Ethane is C2H6, which only has dispersion force, whereas methanol, CH3OH, which has a similar molar mass, methanol has dispersion forces, it also has dipole-dipole forces, and it also has hydrogen bonding. Because of that, methanol has a significantly higher boiling point than ethane, and it also has a significantly higher melting point than ethane. Now we've discussed all of our intermolecular forces, but there is another even stronger force. An ion dipole force is where one molecule will have a permanent charge let's say one compound, one ionic compound, or one ion will have a permanent charge, and the molecule will have a permanent partial charge. We know that ions form between direct electron transfers. So the sodium ion in sodium chloride, remember that sodium reacting with chlorine forms a sodium plus ion or cation and a Cl minus anion. Now these permanent charges on these two ions will attract to the opposite permanent partial charges of a polar molecule. So for example, when we put NaCl in water, the chlorines will actually split apart from the sodiums, or the chloride ions will split apart from the sodium ions. This is because the chloride ions are now having attraction to the partial positive charge that is coming from the hydrogens of the H2O. Similarly, the sodium ions that have a permanent positive charge are now attracted to the partial negative charge that's coming from the oxygen of each of the H2O molecules. Table 12.5 summarizes the different types of intermolecular forces. We have the dispersion force, also known as the London force, which is weak but increases with increasing molar mass of similar families, and it's present in all atoms and molecules. We then have the dipole-dipole force, which has a moderate strength, and it's only present in polar molecules. We then have the hydrogen bond, which is stronger than the dipole-dipole force or the dispersion force. And this happens particularly in molecules that contain the hydrogen bonded directly to the fluorine, oxygen, or nitrogen. And then lastly, we have another type of force that's called the ion dipole force. And that is a very strong force. And that happens when we have a mixture of an ionic compound and polar compounds. Let's try an example problem here. What kind of intermolecular forces are present in each kind of substance? in order to minimize the amount of time that this problem takes, we've already included the molecular geometries of each of these compounds. Great. Pause the video as you try this problem out. All right, let's do this problem together. For NH3, or NCl3, it's already told that the molecular geometry is trigonal pyramidal. So drawing that out, we have nitrogen as our center atom, and then we have a three-sided pyramid structure between our central atom and each of our terminal atoms. Now there is going to be a polar difference between the nitrogen and chlorine for each of these bonds. To look specifically at how much electronegativity difference there is, you have to look at the electronegativity chart. But you'll notice that these do not actually cancel each other out. Only if this is a tetrahedral compound, in this case, would this actually cancel out. But in this case, we have a lone pair that's on top. So in this geometry, the polar bonds do not cancel out. Therefore, we have dipole-dipole. Intermolecular force. We of course have dispersion because all molecules have dispersion forces. And then we need to see if it has hydrogen bonding. Well, we already see that there is no hydrogen present in this molecule. So for that reason, these are the two intermolecular forces for NCl3. Similarly, for NH3, it has a center atom of nitrogen forming a trigonal pyramidal structure with each of the bonds between the central atom and the hydrogen terminal atoms. And for the same reason, we'll see that these partial bonds do not cancel out. And for that reason, we do have a polar molecule. So we do have a dipole-dipole attraction. We of course have dispersion. And then we need to see if this is capable of hydrogen bonding. Remember, for hydrogen bonding, the hydrogen needs to be bonded to a nitrogen, oxygen, or fluorine. In this case, the hydrogen is bonded to the nitrogen. So this molecule has hydrogen bonding. If we look at the compound N3, we already told this is a tetrahedral structure. We can also figure that out. We see that silicon will be our central atom, and it forms a tetrahedral structure with the 4 hydrogen terminal atoms. In this case, all of the polarities of each of these bonds will cancel out because each of these bonds are evenly spaced from each other. And for this reason, all of the polar bonds will cancel. So this is a non-polar bond. Therefore, it does not have dipole-dipole attraction. It does not have hydrogen bonding because there is no hydrogen bonded to a nitrogen, oxygen, or fluorine. So this molecule is only capable of having the dispersion intermolecular force. And then lastly, for carbon tetrachloride, we have a similar scenario as what we saw in number 3. Where each of these polar bonds are going to cancel each other out because of the even distribution of them. So overall, this is a non-polar molecule. So it does not have hydrogen bonding because there are no hydrogens. It doesn't have dipole-dipole. The only intermolecular force it has is dispersion. Let's try another example problem. Which of these substances has the highest boiling point? Hint, these are all nonpolar molecules. Pause the video as you try to figure this one out. All right, by this hint, and by seeing that these molecules are only made up of carbons and hydrogens, so that indicates that we have a nonpolar molecule because electronegativity difference is going to be less than 0.4 between the different bonds, or between different atoms making up the bonds. Because of that, we do not have dipole-dipole attraction. We do not have hydrogen bonding. Therefore, the only intermolecular force is going to be the dispersion force. And as we saw earlier, when we can compare a family of similar compounds, and we see that with increasing molar mass within this family, we have an increasing dispersion force. So number 4 will be the compound with the highest molar mass within this family of similar compounds, which means that this will have the highest dispersion force. And because all these molecules only have the intermolecular force of dispersion, the one with the highest amount of dispersion force will be the one with the highest boiling point. So 4 is our answer. Let's try another example problem. Let's just see if CH, CH2, 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 CH3, if that is miscible with water. Pause the video as you consider this. Right, to determine if two different molecules are going to be miscible with each other, we need to determine if they are both polar. In that case, they're usually miscible. If they're both nonpolar, which in that case they're usually miscible as well, or if one's polar and one's nonpolar. And in that case, they are not going to be miscible. In this carbon-hydrogen structure, or compound, that forms a nonpolar molecule because of the small amount of electronegativity difference of less than 0.4. And H2O is a polar molecule. And we've learned that nonpolar liquids are not miscible with polar liquids. So the answer to this question is that they are not going to be miscible. Now let's look at different types of crystalline solids. We have molecular, ionic, and atomic. So solids may be crystalline, which means we have a well-ordered array of atoms or molecules, or they can be amorphous, which means that they have no long-range order. Crystalline solids can be divided into 3 categories. This is based on the individual units that compose the solid. We can have molecular crystalline solids, ionic crystalline solids, and atomic crystalline solids. Here we see a table where the crystalline solids can be broken into the molecular solids, ionic solids, or atomic solids. For molecular solids, their composite units are molecules, and they have low melting points. So for example, ice is a molecular solid. Crystalline solids can also be of the form ionic solids. Here we have the composite units, which are formula units made up of cations and anions. And these have high melting points. So for example, we have table salt as an ionic solid. And the last category of crystalline solids can be atomic solids, where the composite units are atoms, and these have variable melting points. So for example, we can have an atomic solid made up of just the gold atoms. So the molecular solids are solids whose composite units are molecules. These solids are held together by intermolecular forces that does not include the ion dipole. Ice, which is solid H2O, and dry ice, which is solid CO2, are different examples of molecular solids. Ice is held together by hydrogen bonds, and dry ice is held together by dispersion forces. Molecular solids as a whole tend to have low to moderately low melting points. So we see that ice melts at 0 degrees Celsius, and dry ice sublimes or goes from a solid to a gas state at negative 78 degrees Celsius. Ionic solids are solids that are composed of formula units, and that's the smallest electrically neutral collection of atoms, of cations and anions that compose the compound. These ionic solids are held together by different electrostatic attractions between the cations and the anions of the ionic compounds. Since these ionic bonds are much stronger than any of the intermolecular forces that we discussed previously, so the hydrogen bonding, dipole-dipole, or dispersion, these ionic solids tend to have much higher melting points than the molecular solids. So 2 good examples of ionic solids are table salt, sodium chloride, NaCl, and calcium chloride, CaF2. For example, in NaCl, the attraction between the sodium cations and the chloride anions is what holds the solid lattice together. Because this lattice is composed of these alternating cations and anions in a three-dimensional array. So that is that we have our positive sodium attracted to a negative chloride ion, which is attracted to a positive cation, which is attracted to a negative anion, and so on. And last, we have the atomic solids. And those are solids whose composite units are individual atoms. So atomic solids can be divided into three different categories. We can have covalent atomic solids. We can have non-bonding atomic solids. And we can have metallic atomic solids. And each of these are held together by a different kind of force. So diamond, which is just made up of carbon, is made up of carbon covalently bonded atoms in a structure, is an atomic solid. It's one of our covalent atomic solids. Iron is an atomic solid. And then we have solid xenon, which is another example of an atomic solid. So again, atomic solids can be broken into covalent atomic solids, non-bonding atomic solids, and metallic atomic solids. So with covalent atomic solids, we have our atoms that are held together by covalent bonds. But these will be the same type of atom that's covalently bonded to each other. And these will have high melting points. So silicon is an example of a covalent atomic solid. Xenon is another example. Is an example of a non-bonding atomic solid, which is held together only by dispersion forces. So the atoms are not covalently bonded to each other. They're just held together by dispersion forces. And these type of non-bonding atomic solids will have low melting points. And then lastly, we have metallic atomic solids, which are held together by metallic bonds, these different atoms. And these will have variable melting points. So for example, gold is a metallic atomic solid made up of only gold atoms. So we have covalent atomic solids such as diamond. They're held together by covalent bonds, as we said before. In a diamond, each carbon atom forms 4 covalent bonds to 4 other carbon atoms. And they form a tetrahedral geometry, each of these central carbon atoms. And the structure will continue throughout the crystal. So in a way, we can think of the diamond crystal as a giant molecule that's held together by these different covalent bonds. So since covalent bonds are very strong, these covalent atomic solids have very high melting points. Diamond, for example, has a melting point of about 3,800 degrees Celsius. With our non-bonding atomic solids, such as our solid xenon, They're held together by relatively weak dispersion forces. So xenon atoms have stable electron configurations, and therefore they do not form covalent bonds with each other. So solid xenon, like other non-bonding atomic solids, end up having a very low melting point because of the relatively weak dispersion forces. So solid xenon's melting point is about negative 112 degrees Celsius. And then for metallic atomic solids, such as iron, silver, and lead, they have variable melting points. These metals are held together by metallic bonds that in this simple model consists of positive charged ions and a sea of negative charged electrons. And these metallic bonds can vary in strength. So for each of these four, let's identify them to be either, so each of these four solids, let's identify them to be either molecular, ionic, or atomic. So for number one, we have H2S. H2S is composed of two or more different types of atoms. These are covalently bonded. So this is a molecule or molecular. For number two, we notice that potassium is a metal and chlorine is a nonmetal. So potassium chloride is an ionic compound. So this is an ionic solid. Let's skip to number four. Number four is between two nonmetals, two different nonmetals. So this is a molecular solid. And then lastly, let's look at number three. Number three is what we've learned to call a diatomic molecule, but classifying them as classifying N2 as either a molecular, atomic, or ionic solid. Remember that we've learned that we can have what is considered a covalent atomic solid. That is, that we can have atoms that are covalently bonded to each other as long as those are the same atom. So these nitrogens, because these nitrogens are the same atom, bonded by one covalent bond, this forms an atomic, or specifically a covalent atomic solid. Lastly, let's look at water and why it makes such a significant molecule. So water has a low molar mass, specifically 18.02 grams per mole. Yet it's a liquid instead of a gas at room temperature. We see that water has a relatively high boiling point, and this can be understood by examining the structure of the water molecule. So water molecules have an electron domain geometry of tetrahedral, but the molecular geometry is bent. So the oxygen has a partial negative end, and the hydrogens have a partial positive end. the bent geometry of this water molecule, and because the OH bonds are so highly polar, this results in a molecule with a significant dipole moment. Because this water molecule has two OH bonds, this allows a water molecule to form strong hydrogen bonds with other water molecules. And this results in a relatively high boiling point. Because of this high polarity for water, it also allows it to dissolve many other polar and ionic compounds. Remember that polar and polar are miscible. So in water, other polar molecules will dissolve into water or be miscible in it. Ionic compounds, many ionic compounds will also dissolve into it, such as sodium chloride. For this reason, water ends up being the main solvent in living organisms, and it transports nutrients and other important compounds throughout the body. The way the water freezes is also unique. Unlike other substances, which end up contracting upon freezing, water actually expands upon freezing. And because of this expansion when it freezes, ice ends up being less dense than liquid water. For this reason, ice cubes and icebergs float on top of liquid water. So the frozen layer of ice that's at the surface of a winter lake will insulate the water inside of the lake from further freezing. If this ice layer were to sink, it could kill bottom-dwelling aquatic life and could allow the lake to freeze solid, which would eliminate virtually all aquatic life in the lake. So as a summary of this chapter, we looked over properties of liquids and solids. We looked at surface tension and viscosity that happens from the high intermolecular forces in liquids. We looked at phase changes, evaporation, condensation between the liquid and gas, melting and freezing between the solid and liquid, and sublimation between the solid and gas. We also looked at the different types of intermolecular forces and the different types of crystalline solids, and we looked at water and why it's so significant, or it has so many significant properties. That's due to the intermolecular forces that are present in water.